Welcome, everyone. So I'm Eric Bergener. I work with Virsto Software, and we're going to spend a lot of time doing a deep dive today on some of the storage problems that you're likely to run into in virtual desktop environments. Before we get started, let me just ask briefly of the people in the audience. So how many people have actually worked on at least a pilot deployment on the VDI side? Okay, so we've got about half, it looks like. So many of you may have seen some of these problems. Some of the problems that I'll talk about actually don't become apparent until you start to deploy at scale. So hopefully you'll be able to take away also some knowledge that will help you avoid some nasty surprises potentially in the future. What I'd like to do today is talk a little bit about some survey results we completed about 6 months ago on people who had VDI projects underway. Then we'll take a really close look at some of the storage problems specifically in these environments, what the implications of those are. And then we'll talk about some of the industry responses, the pros and cons that you have with each one of those. And end with a quick look at some best practice suggestions for deploying storage in these environments. So this was a survey that had a sample size of 500. It was international in scope. So this gives you an idea of what some of your colleagues are saying out there. There's a lot of potential work going on in the VDI arena. Of the respondents, over half of them had already taken a look at projects, but interestingly, almost half of those people had reached a stall point. Typically that stall point came when they finished pilot and started to roll things out at scale. The reason why the projects stall seem to be very storage centric. So of the top 4 responses that we got, 3 of these, storage cost prohibitive, inadequate desktop performance, and overall costs too high, could be directly related to storage issues that they ran into during rollout. The drivers, I thought this was an interesting piece of data, although it doesn't necessarily relate directly to storage, but interestingly, 43% of the people think they're actually going to lower the cost of desktop environments by doing this. And certainly what we found in practice is that that's a very difficult objective to achieve. In many cases it's because of storage, but there's a lot of other reasons why it's very difficult to match that. The biggest benefit from my point of view is streamlining the endpoint management and all the operational savings that are associated with that. But still, this is the perception that people have, that they're going to be lowering the costs on the desktop side. So let's talk a little bit about what the storage performance problem is at a base level. So first, think about virtual environments. This could be virtual server or virtual desktops. What's happening when you move from a situation where you've got a client-server config, dedicated application running on a dedicated host, with a dedicated application and storage, to an environment where you have multiple applications running on the same physical host? You get a significant increase in the randomness of the I/O patterns in those environments. And if you think about how spinning disk operates in writing, it does not perform very well as randomness increases. So the rotational latencies and the seek times on average for the I/Os go up very significantly because of the randomness of these environments. And this storage slowdown can be as much as 30 to 50% at a macro level. So it has a huge impact on the number of spindles that you need to meet the performance requirements that you have. Typically, when people start out in the virtual world, they are using some of the sizing algorithms that they had worked with in the physical world. And these just don't map because of this randomness issue. So the randomness is really the first issue. There are a couple of other related issues. Because they're already starved for IOPS, people tend not to look at thin provision devices, because a thin provision device on average is going to require anywhere between 4 and 7 additional write IOPS for each write IOP that's requested from the application point of view. So the back-end storage is working a lot harder than it looks like it's working on the front end. So when people come up with the idea, or they look at the idea of thin provisioning storage to save space, there's actually an attendant increase in the number of spindles that would be required to meet a given performance level because of that thin provisioning. So there's a trade-off here. Another area that has cause some issues out there is the fact that if you're going to be operating with block-based storage, then you probably got to have some significant storage expertise that will need to come into play as you're provisioning VMs or deprovisioning them. That's because LUN level management is going to really be the order of the day. One of the reasons why people take a look at NFS and file servers is because it's a lot easier to manage file shares in these environments than it is to manage LUNs. And if you think about the fact that server administrators now, really the focus is shifting to them in terms of trying to manage the environment comprehensively. Many of the smaller companies don't even have a separate storage group. Storage is being managed by the server administrators in many cases. Many of them do not have storage expertise. So trying to manage things at the LUN level can be a complexity problem. Okay, I talked about the macro impact there, 30 to 50%. Now, that's just the standard virtual environment. Now, let's talk about why VDI is a lot more difficult. So, number one, if you think about Windows desktops, XP, Windows 7, these are operating systems that expect to touch the disk a lot in doing what they're doing. The expectation was they had a local device that they owned solely, and if you move the infrastructure to a shared setup, which is what you're effectively doing in hosted VDI environments, you're really changing the dynamics here. The Windows is still going to want to touch the disk a lot, but now you're going over a network to do that. So there's additional latencies that are imposed, and those are significant because you're touching the operating system so much more than, let's say, a standard server environment would be doing. Okay, second point, write intensivity. I don't know if you attended any of the other sessions today, but I saw some numbers that were pretty consistent from what we've been seeing out in the field, that if you think about one of the changes of the virtual world, not only do you have this increased randomness, but the I/O patterns are also significantly more write intensive. And spinning disks, again, don't handle writes as well as they handle reads. So this is another thing that's detracting from the performance that you're going to get out of your existing storage in these environments. And often a surprise, again, if you're thinking about, the sizing was based on what I saw on the server side in the physical world. You've also got things like boot, logon, logout, application storms that generate significantly greater peak IOPS requirements in VDI environments than what you've ever seen in most server environments. So when you size your storage configurations, people are typically forced to size for the peaks. And you have some significant differences here. It can be as much as 10x steady state IOPS requirements versus what you're seeing during a storm situation. Now there's different types of storms. There are read intensive storms. So boot, login, application tend to be very read intensive. And there's also write intensive storms. Logouts are a perfect example of that. And as you're looking at what you need to do in these environments, you need to think about both of those. Now, the final point I'll make on desktops is there's a scale issue difference when it comes to provisioning desktops relative to what you're doing on the server side. If you think about having to spin up a new server VM, that's something that you may not do that frequently, possibly a couple of times a day or a couple of times a week. In the desktop environment, so let's say you're doing a desktop deployment that has 1,000 desktops. So it's not just the initial deployment, but it's every time you need to go in and do an image update against the operating system disks primarily in these environments. You're going to have to clone and roll out all of those desktops again. So if you think about the trade-off I mentioned briefly earlier about thin provision disk, which you can create very rapidly but has a performance impact, versus what many people end up using in these environments, which is a thick or fully provisioned device, it takes longer to create those fully provisioned devices because the storage subsystem has to go out, allocate the blocks, zero them all out, get everything ready before that storage can be used even the first time. Now in thin provisioning, obviously what they're doing is they're separating the logical creation of the device and all of this other housekeeping that goes on a regular basis. That's that 4 to 7 additional IOs that I mentioned a little bit earlier on the thin provision side. That's what's happening, is effectively each time you write to that device, as you're expanding it out, you're going to be going out, allocating new blocks, zeroing those blocks out, updating a logical to physical mapping, and only then do you actually perform the requested write IOP that you got from the application side. Now that's true up until the point where you've written to every one of the blocks within that device. And so you sort of see this chart of the performance increasing on a thin provisioned disk up to the point where all the blocks get written. Then it tails off. Unfortunately, in the implementations we've seen out there in Hyper-V, VMware, and Xen Server, that never starts to approach a fully provisioned disk. So you've still, even once all those blocks are written, you still have a performance issue. So how that translates on the provisioning side is that if I have to thick provision 1,000 disks every time I do a refresh operation against Windows because of a patch Tuesday, that's an operation that could take many hours or days, depending upon how many desktops I have. And that's another real time sink that a lot of people don't think about in these environments until they've actually started to use them. Okay. Now, as you think about sizing storage for these configurations, there are other issues that you need to take into account besides just what my IOPS requirements are generated from the application side. So there's a lot of other things that are going on. One I want to comment on is the difference between floating and dedicated or non-persistent and persistent desktops. So typically in these environments, you'll have a higher storage requirement on the persistent side. So if you're looking at deploying and your end users have requirements for customization, people often automatically think that that requires a persistent desktop. You can see with a lot of the newer tools that are coming out from third-party vendors, that's not always necessarily true. You can often create the perception of a customized desktop while you're actually using a floating type design. But at any rate, there are certain power users that absolutely do require persistence, and power users aren't the only requirements that drive that. You clearly are going to need more storage in the persistent case, so that will impact what you're doing. One of the nice things about VDI is you can centralize a lot of the operations that you have to do. Antivirus scans are one thing that are done pretty much on a regular basis, very read intensive. You think about the antivirus scans before were being done on dedicated IDE disks out on the laptops or the desktops. Now all of that is moving to this shared storage infrastructure that you've put in place. So when you run antivirus scans, there's going to be a huge increase in read IOPS to be able to handle that. It also means that you want to schedule very carefully when you do that, because that's going to have a huge impact on the system that will impact everything else that's running on that same storage system. Okay, how many times a year do I need to refresh the desktops because of either a change in the golden image, a patch, something of that nature? What Microsoft will tell you if you're using XP or Win 7 is that you should expect to do this 8 to 16 times a year. Now that's based on, what they're talking about. Most people don't do it that often, and primarily they don't do it that often because it's so onerous to go back and recreate all of the desktops that are out there. Because effectively you have to remove the OS disk or what you might be using as a VM master, recreate the new one, clone it, reattach them to all the devices, then boot them from there. So if you do this more rather than less, you tend to care a lot more about being able to create that storage very quickly, which again pushes you back to that decision I talked about a little bit earlier, which is thin provision devices, I can create them very rapidly, they don't offer very good performance. Thick devices offer better performance, I need fewer spindles to meet the requirements, but it takes time to provision those. Okay. Your desktop data. So let me ask a question of the audience. In your physical desktop environments, were you guys depending upon the end users to perform the backups? Let me see how many people were depending on users to perform the backups. Okay, so for those of you who weren't, was the assumption that there was no backup going on at all? Is that what I'm taking to read from this? Okay. All right, so one of the things that vendors will tell you when you move to a VDI environment is now you've got this centralized data. It's going to be a lot easier for you to back it up. You've got sophisticated resources that understand how these applications work. So that's true, but there's going to be a huge impact on the storage subsystem while you're running those backups. And again, that's going to impact everything that's going on against that storage subsystem. See, one of the things that you really need to realize conceptually about these environments is the old physical environment, what a single desktop did not impact anybody else from the point of view of storage because they had their own dedicated device. Shared infrastructure, it potentially has a huge impact for things like antivirus scans, for backups, and some of the boot and log on, log out storms, etc. So if you decide you are going to back data up, one of the things that you're going to need to take into account is what are the IOPS requirements for doing that? And scheduling is obviously another thing, just like with the antivirus scans. Okay, another question. So this one comes up in almost every virtual server case and comes up a lot less often in virtual desktop cases. But there are still environments where you want to use capabilities like failover. And if you're looking at certain technologies like solid-state disk deployed at the host to be able to speed up the environments, you're effectively cutting out an ability to support failover. So again, that's another trade-off that you need to be aware of. In most cases, individual desktops are not set up for failover. We've had some customers where they have a very small number of executive desktops that they do want to enable that with, but generally people don't do it. The assumption is the desktop goes away, they're just going to try to log back in and get redirected to another host. So that's not an issue in VDI environments nearly as often as it is on the server side. Okay, but again, you need to ask yourself that because that's going to limit what your storage configurations look like if you do have a requirement to support things like failover. Okay, so I made a few comments about this a little earlier, but I really want to make sure people understand what the options are here. If you look at native hypervisor storage options, in each of the major environments, vSphere, Hyper-V, XenServer, there are three options that you have. You can create a fully provisioned disk. That's that thick or fixed VMDK, fixed VHD on the left-hand side. You can see what the pros and cons of it. High performance, takes a long time to create, doesn't use space very well. You've got a thin provision option, thin VMDKs on the vSphere side, dynamic VHDs with Hyper-V. Performance is not very good, but they use space a lot more efficiently, and you can create them faster. So in environments, desktop environments where your IOPS requirements are relatively low, thin provision devices can potentially meet the need. And it's very nice to be able to spin these things up very rapidly because of the refresh operation requirements. But in most cases, these are potentially a problem, which is what's driving people to look at implementing SSD in their systems to help with read performance issues, etc. Okay, and then the third type you have is for single image management situations where you want to create a single golden master and roll out hundreds or thousands of desktops from it. So these are thin provision devices. This is like a linked clone on the VMDK side or a differencing disk in Hyper-V. They basically have the same problems that you have with a thin device because they are in fact a thin device. It's just one now that has a relationship to some number of other child clones. The conundrum is that you need to pick one of these when you're rolling out a desktop environment. And what you really would be interested in is you want a high-performance device that's thin provisioned and can be also instantly created. That would be the best of all possible worlds in this case. Now, I put this up here because when I make the comments on that previous slide, I've noticed in previous presentations a lot of people haven't actually done a direct performance comparison between a thick VMDK and a thin VMDK. So I want to actually let you guys see what the impact is. Now, I happen to run this on ESX, but this is not an ESX problem. This is the impact of thin provisioning in these environments, and we've seen the same exact differentials on the Hyper-V and the XenServer side. So what I've got here is, on the far left, is a raw device map disk, okay, which is basically the most performance I'm going to get out of the device connected up into a vSphere environment is going to be a raw device map disk. They're a lot harder to manage, so people tend not to use them very often. But that sort of gives you the maximum threshold you could get out of a set of devices. The second set of columns, the blue and the red. So the blue is a thick VMDK, And as soon as I attach a snapshot to it, this is an ESX copy on write snapshot, you can see the performance on that drops by about 90%. Now, it's not just the snapshot I'm getting poor performance on, I'm also getting poor performance against the source device that I created that snapshot on. Now, the assumption that we make here is this is what it looks like as soon as I create that thin provision device. So we haven't run it for some amount of time, in which case that red bar is going to start to go up, but it will never approach the top of the blue bar. If you create a thin VMDK, whether it has a snapshot attached to it or not, you're basically operating at that lower level. That's the third set of bars there. Okay, so I just wanted to make sure people understood that this impact is potentially huge. If I'm getting 90% less IOPS out of each one of my spindles, I need to either buy a lot more disk spindles, or I need to go invest in something like SSD or read-based caching to solve those problems. Now I'm going to leave the fourth set of bars off for a bit here. Okay, so what has the response been in the industry? There have been three basic classes of response. The first one is, hey, you've already got a storage array from vendor A, you need to go buy a lot more spindles. And you can run the calculation pretty quickly by taking a look at, there's a set of numbers that'll tell you how many IOPS you're going to get out of a particular disk device. And it's not just the vendor's rating of the device, but it also has to do with what RAID level you're running that device in, whether you're running thin provisioning on the back end or not. There's a few other things that generate an additional need for IOPS that the storage subsystem has to manage. But you can ultimately get to a point that says, if I need 20,000 IOPS and I'm getting 100 IOPS per spindle, then I can figure out exactly how many spindles I need. So this is a very expensive way to solve the problem. This is basically the same approach that people have used for many years on the physical side. But because the performance degradation issue was not nearly as big as it is in the virtual world, over-provisioning your storage means that you might have bought maybe an extra 15 or 20% of devices, not potentially 50% more devices. Okay, another approach is, well, maybe I had SATA drives, or maybe I had 10K RPM drives. What if I go to a faster drive type, upgrade to Fibre Channel 15K RPM, or maybe I buy an enterprise class array that has got a lot more storage bandwidth that I can work with. So that's another potential way. Disruptive, expensive, but if you have enough money, you can clearly solve the performance problem with these types of options. Another approach has been to leverage SSD. And I think this first came to prominence with folks like Fusion IO, and you were looking at putting an SSD card in the host. Great read performance out of these environments. That one will cut out any ability to support any kind of HA on the back end if you do need that. There's a way to use SSD, though, that you can continue to support HA, and that's by putting SSD caches in the SAN. So you'll see a lot of the newer equipment from vendors will have a little rack space where you can put some SSD devices in there. So that's true with all the majors, EMC, HP, IBM. They've all got that option, so you can create a mix of storage devices where you've got a small cache of SSD and then you've got slower devices spinning disk on the back end. That SAN-based approach is interesting. Actually, the host and the SAN-based approach both have another nice impact, which is if I have SSD on the front end, I typically need a lot fewer spindles on the back end to meet IOPS requirements, especially if reads was the problem. So this is a nice way to reduce the number of spindles I need to buy in certain cases. Now you need to take into account how much physical capacity you actually need, because you're not getting a lot of capacity when you're buying SSD. But capacity tends to be sort of the third thing you consider when you're sizing configurations. Okay, so let's talk a little bit about what you should be taking into account when you are sizing storage configurations. So the number one driving factor is going to be the IOPS requirements. But it's not just steady state. So if you think about the other things that are going on, we talked about peak I/O requirements due to things like boot storms. There's read versus write ratios. And typically what you're going to need to solve for is the peak write requirement, because that's going to be the highest level requirement that's going to need the most spindles to get the problem solved in these environments. Now what's sort of unfortunate about SSD is really great at boosting read performance. It's a lot less good at boosting write performance, although it will boost it over spinning disk. And it's even worse at boosting random write performance. So now if you remember back to the slide we talked about very early on, the I/O patterns that are being generated in VDI environments in steady state are extremely random, extremely write intensive. So the speed up that you get from SSDs, if you're looking at the numbers that are quoted by the vendors in their specs, that's all read pretty much, unless you've specifically focused on what the write is. So that's going to be a shock if you think that you're putting a device in there that's going to deliver 6,000 read IOPS and you're not seeing even a tenth of that out of the random write side with that device. And that device is not going to speed up writes at all unless it's been implemented with a write-back cache. So the MLC devices that are a lot more affordable that you see, MLC, NAND Flash, tend not to have write-back caches. They tend to be write-through, which means that they give you a good read performance speed up, but they do absolutely nothing for writes. And if writes are really your problem in the VDI environment, that's something you should be aware of before you invest in SSD devices. Okay, the second thing you need to take into account has to do with the data protection overhead, specifically RAID. And there's different calculations for different RAID levels, but basically what you're doing is adding the need for additional IOPS as you're implementing RAID levels. So even though this doesn't do anything for speeding up your application, it's something that you need to account for as you're building your storage array, because the storage array has to be able to meet the requirements for laying down the extra writes for like a RAID 5 or a RAID 6 stripe or a mirrored stripe, things of that nature. I'm not putting any of the formulas up here that will show you how to calculate that, because those are things you can find online pretty easily for the different RAID levels. But that is something to take into account. These can be, easily can be 10 to 25%. And in fact, in RAID 1, if you're running a 2-disk array, it can be 50% increase in write IOPS. So that can be potentially huge. That's one of the reasons why most people deploy a mix of RAID configurations in their storage when they do VDI. Because if you think about RAID 1 is really optimized from a performance point of view for writes, but it's got a 50% write overhead associated with it. RAID 5 tends to be a lot smaller. Depending upon how many disks are in that array, it's going to be a 1/n type of a performance hit. RAID 5 is pretty good at reads from the point of view of its RAID. So what we'll often see is a very small amount of storage configured for RAID 1 type configs, where you might be putting, you might want to put the writes in those kind of locations. And most of the rest of the storage that's handling the reads might be in a RAID 5. So there's less of an IOPS requirement on the RAID 5 side. Okay, the third thing that you need to take into account, and often this one is just a check, is capacity. And the reason why I say it's just a check is that after you've figured out how many spindles you need to meet the first two requirements, you generally have way more storage capacity than you need to meet the third one. So you need to make sure that you've got enough, run a quick check, but that's probably not going to add to your ultimate spindle requirements, because you're going to be way over provisioned from a capacity point of view, which is one of the reasons why people always ask about thin provisioning. Hey, if I've got way more capacity than I need, can I use thin provisioning? But again, remember, that's going to impact the number of spindles you need for number one. Okay. So one of the things I really hope that you'll take away from this is that it's not read IOPS that matters, it's write IOPS that matters in VDI environments. That's clearly what you're going to need to look for. So let me give you a couple examples of the ratios. Boot storms, which are read intensive. Often the planning number you see is 90% reads, 10% writes during a boot storm. During steady state, that number generally flips. And it's not uncommon at all to see 90% writes and 10% reads in steady state. So if you're buying SSD to meet your performance requirements, you need to really make sure that it's meeting the problem you have, because your problem is probably writes. And you got to make sure that however you implement SSD, if you decide to do that, it's going to address that issue. I mentioned the difference between a write-through and a write-back cache. So what a write-through cache does is it basically does not send a write acknowledgement back to the application when the write hits the cache, it sends it through after that's been written through to spinning disk on the back end, which means that the latency for that particular write I/O is actually a little bit worse than it was if you didn't have that cache sitting there. Now, a write back cache is implemented in such a way that it's persistent. So if you have a host failure, anything that's been written to the cache will be there once you recover that host, which also means that you can support things like failover, because you need to access that to be able to replay or gain access to some of that data that's sitting in the cache but has not been written through down the disk. So if you think about what the cost differential is between what I would call enterprise SLC NAND flash based SSDs and what you're seeing on the MLC side, which is feasible to use for read caching. Well, I know it in dollars, so let me see if I can do a quick conversion here. It's about twice as expensive to buy the SLC NAND flash with the write back cache than it is to buy MLC that's just a write through. Okay, so yeah, you can buy something that'll solve the problem, but it's an issue of how much money do you have to throw at this problem. Okay, this gives you an idea of where you might want to use particular types of fast and slow storage, read and write intensive. So we talked about the read intensive ones quite a bit. Write intensive ones, so steady state log outs at the end of the day, a lot of writes go to the back end storage when people are logging out, so that's a huge impact. And depending upon how you're performing backups, if you are performing backups, this could also put a lot of strain on the storage system. Golden masters. So I mentioned single image management a little earlier. And this is actually a great place if you have access to storage tiering to be able to lock down. The golden master is the device that you're creating a bunch of copies from that you're going to actually mount on the desktops out there. And you've got implementations available in VMware, linked clones, that basically put the shared blocks in high-performance storage and every read that goes to those, and there's going to be a lot of them because that's usually the OS disk, so you're touching that a lot from a read point of view. That's a great way to speed that up. So that's a good place where if you've only got enough money to spend a little bit on extremely fast storage, which that depends on your environment. It could be 15K RPM fiber channel, maybe it's SSD, maybe it's buying extra DRAM because you've got an ability to do some sort of DRAM read caching. That's a good place to use it, is on the golden masters, because that impacts the performance that all of the desktops see. Okay, so this is just sort of so you guys have an understanding of what some of the numbers we're seeing out there. I'm actually going to show numbers that are both from VMware and Citrix in terms of their recommendations for IOPS requirements on different desktop types. So these first numbers here are from VMware. And you can see that the burst IOPS requirement is 10x the steady state. Okay, that is a huge differential. And unfortunately, you've got to provision storage somehow to plan for that peak, even though most of the time you may be running significantly less from that point of view. The numbers from Citrix are a little bit lower. I didn't find anything on XP that was up to date with them, but those are the numbers I've seen quoted from Citrix in technical papers on Zen Desktop. Now, your environment, ultimately this really depends upon what you're doing with your desktops. So I would highly recommend, and in fact it's one of the best practice suggestions at the end, is you absolutely need to pilot these environments correctly, understanding what the problems are, so that once you get a set of relationships between the storage, the network, CPU memory resource, etc., you're going to be able to scale that appropriately so that you can forecast what your rollout costs are going to be. A very common problem that we see in probably 80% plus of customers is that they don't think a lot about provisioning the storage for the pilot because it's small. They only may have 100 desktops. They throw a small array at it, its storage is way over provisioned, everything looks like it's fine, and then when they start rolling it out, then they really come up against the number of, okay, this storage, this is really how much this storage can support. And they didn't have an understanding of what that actual relationship was, And that's why so many of them run into these stalled projects that we looked at a little bit earlier in that VDI survey we had, is that they haven't gauged this accurately during the pilot. And so they just get to a point where they don't have any more budget left to buy more spindles to address the problem. So you really need to understand what your environment is. Now, I heard this morning I was in an earlier presentation and I heard a number of 2.2 IOPS per desktop was quoted. And I was a little surprised, and I asked the guy after the presentation, you know, what that was, and he said, hey, this is assumed to be very light use, not even an office user. So there's a lot of variability. Your mileage will vary. You really need to understand what your environment looks like. But again, these are the sizing guidelines that VMware and Citrix are putting out there. Okay, so as if that's not complex enough, there's a great blog that Ruben Sprout put out, and it generated a lot of comments. And this is the web access for it. I think reading this article is a great way to understand the complexities associated with sizing. What he actually tried to do was come up with some real-life numbers so that you could actually see in a customer setting what it might look like. And most of the comments after it were disagreements with, well, those numbers aren't right and mine are different. But I think what it does a great job of, if you read this, which will be about a 10-minute investment of your time, you really get an understanding of the complexity of these environments. And that's one of the reasons why I think it's very important that when you're sizing these configurations, you absolutely want a savvy storage person involved in this, because this is very difficult to figure out. I mean, there are formulas, but there's so many of them, and there's so many interrelationships, and the variables vary as that changes, this changes, and it's very complex in these environments. If you have enough money to over-provision, then you don't have to do that, right? And you just throw a bunch of storage at it and the problem's solved. But if you have budgets that you have to deal with, which obviously most of us do, it's going to be good to understand exactly how much storage you need and how that's going to meet your environment. I mentioned the primacy of right IOPS, so I don't need to go over that again. And this idea of running the proofs of concept so that you can accurately forecast what your deployment costs are going to be in these environments. So that's a very critical thing to take into account. Okay, so from a business point of view, you don't have any really very good choices. Either pay a lot of money unexpectedly. You have to choose between, do I want performance, do I want fast provisioning? So it's a conundrum that, you know, there's no good answer for out there. All right, so I want to shift tactics a little bit here and talk about a new idea that many of you may have seen in the market called a storage hypervisor. So there's probably 6 or 7 vendors that now have a storage hypervisor in their offerings. The basic concept here is that if you look at what server hypervisors did, they basically did 2 things for server resources. They allowed you to increase the rate at which you could utilize server resources that you already paid for, and they virtualized those resources to make them a lot easier to manage, giving you the opportunity to move things around, etc. Okay, but there's those 2 things, improving the utilization and addressing the virtualization of those resources. Storage hypervisor would do pretty much the same thing for storage. Now, if you think about increasing resource utilization, let me give you a perfect example that sort of lays this concept out well. If you buy a high-end fiber channel 15K RPM disk, you're probably going to have a tech spec on there somewhere that says it delivers between 18 and 200 180 and 200 IOPS for that device. If you play around with IOStat or perfmon in your environment, you can actually take a look at what that device is generating in a VDI deployment. You may see that that device is actually only delivering somewhere between 30 and 45 usable IOPS to your application. Okay? That's the impact of the performance slowdown. That's this random write intensivity that's causing that. But that device is obviously capable of doing a lot more than 30 IOPS. So the idea here is, what can we do to fundamentally change the way that the hypervisor handles I/O to be able to get a lot closer to that theoretical max number out of those devices that you already paid for? Very similar to the server side, where I had CPU and memory resources that I may be taxing to 10 to 12% utilization when they were sitting in a dedicated location. So it's a good analogy between these two here. Now, if you can actually do something like that on the right-hand side, it's not only a performance implication, but there are also a lot of other implications on the capacity consumption and on the management side, which we'll take a look at here. So let me reference again something that Ruben Spruit said in his presentation this morning. He was talking about multiple ways to address some of these issues, and one of the ways was take a very random stream and turn it into a sequential stream. Okay? The way to do that is with a log architecture. And so many of you may be familiar with transaction logs in database environments. So this idea is conceptually similar to that, but there are some significant differences. What this is basically going to do is take this stream that before was very random and was writing out to all these different devices out there, and it takes 100% of the writes and it puts them into a log device. So the performance that the VMs on that host see is the performance of the log device operating in streaming mode. Streaming mode gets you back to that 200 plus IOPS that you saw on the tech spec for that device, if it was a fiber channel 15K RPM device. Then what happens here is all those writes, after they're acknowledged, get asynchronously destaged to a shared storage area that handles all of the reads in these environments. So what you've got is a dedicated spindle that's operating in sequential mode 100% of the time, determining the write performance. And you get all the other spindles delivering reads. Dedicated usage, okay? One spindle does writes, all these other ones do reads. So this provides performance improvements in a couple of ways. Number one, that log device is going to give you that 10x increase in terms of the actual IOPS the application sees. And that number is actually on the conservative side. We'll take a look at that a little bit later. But this is a huge way to speed up what you already own. You don't have to buy any new hardware if you use a log architecture. Okay, so this concept of changing it from random to sequential, that's really what the log device does. Now that you've acknowledged the writes from the log point of view, you have some additional time to do some interesting things in how you lay data out in the shared read area. So you can actually set things up to maximize sequential read performance on a VM by VM basis, which gives you a smaller performance improvement, more on the order of 20 to 30%, but that's on top of the storage that you already own. So this, you can see that this is really geared towards turbocharging write performance and only does a little bit for read performance. Don't have to buy any more hardware, but one of the other really interesting implications here is that if that dedicated log device is sitting in the SAN, then this model supports failover. And potentially you can put SSD in as a log device. So you could use spinning disk or SSD as a log device. As long as it's in the SAN, you can support failover. So this has some interesting implications for VDI. It also applies in the virtual server world because of its ability to support HA. Now, let's take a look at how this might affect the peak I/O requirements on the write side. So these log devices are very small. And you've probably seen this if you've worked at all with databases, but that device is generally 10 gigabytes in size. If you think about the size of a cache that you're using, let's say higher performance storage, SSD, generally that's calculated at a percentage of what your primary storage back end is. If you've got 35 terabytes on the back end, you typically need to deploy somewhere between 2 and 4% in SSD capacity in VDI environments. That's sort of the starting sizing that you'll get from vendors like EMC, IBM, HP. So that's a lot of capacity. That could be 14, 16, 18 SSD drives. And these drives are 6,000 pounds plus in cost for like a 200 gig EFD that would fit into a Clarion box. So they're not inexpensive. The log has a great ability to absorb I/O spikes that are short in duration without any performance impact on the system because it's draining out to the shared area at the same time that it's writing to the log device. And if in fact the log device flows over, then you can make the log device a little bigger. Make it 11 gigabytes instead of 10 gigabytes. So you've got a nice little way to adjust for this. And this will absorb write spikes without hardly any impact on the performance. In fact, if you make the log a little bigger, there'll be no impact on performance. So this is a really interesting model. Now, that sort of identifies what they did on the database side. What's more interesting in the VDI environment is now that I have some extra time as I'm destaging stuff to a shared area, I can do some other interesting things besides just maximizing the sequential read performance based on how I lay data out. I can do things like thin provisioning of storage that is sitting in the back end here, and they still appear to operate at the performance of the log device, which means that I can have thin provisioned disks that I can instantly provision, and they're going to outperform raw device map disks. Okay? That's that combination I mentioned a little bit earlier when I said, wouldn't it be nice if you could have a high performance, space efficient, instantly provisionable storage device? Well, this architecture gives you that. And in fact, it not only gives you that from the thin provisioning point of view, but it allows you to run snapshots on the back end. And those snapshots, again, are going to outperform any kind of a thick VMDK or a fixed VHD that you would have. So this has some real nice impacts in terms of comprehensively speeding up the performance of the system. Okay, so I wanted to make a couple of comments about us as a vendor, and then I have a few more generic comments I want to make. So what Virsto does is we provide a software-based storage hypervisor, plugs into your ESX or your Hyper-V host, and implements this log architecture that we just took a look at. What we see in customer sites is you're going to get a speed up on existing storage of at least 10x. Many times it's as high as 50x, depending upon what they're doing. It's all thin provision storage. We can provision thousands of clones in literally seconds, regardless of the size. And it also allows you to manage all the storage just like you're managing file shares, even though this is actually sitting on block-based storage. So remember I mentioned a little bit earlier, one of the reasons why people look at NAS is because it's a lot easier to manage file shares in these environments, specifically when you're spinning VMs up and down, like you're often doing in desktop environments. So that's an ease of use kind of a feature there. What this architecture basically does is turn that random I/O into a single sequential stream. That's where the performance speed up happens. Everything writes through to a shared area. It all gets read. So very similar to those slides I talked about a little bit before. This implementation also supports storage tiering. So you've got an ability to set up small tiers with higher performance storage if you want to lock golden masters down there, that type of thing. And it's pure software. So you don't have to buy any SSD. If you buy SSD, we'll speed that up as well because we get that operating in sequential mode. But it'll speed spinning or SSD up. Supports multi-nodes, failover against shared SAN configurations. That's the way that it's designed. Now on the management side, this basically plugs into the hypervisor transparently. So all of the workflows that you're already using for things like VM provisioning and deprovisioning still operate the same way through the same wizards. Okay, the only guy that actually knows this is installed in the environment is the storage guy that installed it. Outside of that, there's nothing to learn on how to use it. Okay, so now I want to shift back into generic mode, now that you kind of know a little bit about what we're doing. So SSD cache versus SSD log. This is something I'd like to talk a little bit about here. I mentioned what the sizing guidelines are that you tend to see from the major array vendors, 2 to 4% of the storage back end for an SSD cache. Typically optimized for read performance. If you want to have write performance out of them, you've got to make sure you've got a write through cache set up there. Don't support failover, it's in the host. And then another thing that I've seen talked about in some technical presentations, not so much here, but at some other events I've attended over the last couple of months, is that when you buy the read IOPS speed up with SSD, what you're not really going to get that 5,000 or 6,000 IOPS speed up. What you're going to get is it's going to move the bottleneck from storage to whatever the next bottleneck in the system is. So this is sort of the Amdahl's law realization. And that next bottleneck, which typically is going to be something in the operating system, is not going to be anywhere near that 6,000 IOPS speed up that you thought you bought with the SSD device. So the reason I'm mentioning this is that typically when people do a pounds per IOPS type of a calculation against SSDs, they're going off the tech spec, not what they're actually going to get in their environment, which is likely to be significantly less because of whatever the next bottleneck they're going to hit is. So what this would lead someone to want to do is deploy as little SSD as possible to be able to get the speed ups that I want in my system. So a cache is not a very efficient way to do that. A log is a very efficient way to do that. And I think I already mentioned that, you know, two great places to use SSD would be in a tier 0 where you lock in golden masters, or in a log device. And if the log device is only 10 gigs per host, you could support a 16 node cluster with one 200 gig EFD. Very efficient use of SSD capacity. Now, what I want to show here is a calculation actually from one of our customers who had sized their environment, what they needed on SSD against a 35 terabyte back end. And they were told by EMC that they were going to need to buy 14 of these 200 gig EFDs. When they put our software on, they needed 4 of them to outperform what they were going to get on the left-hand side. So that was a pretty significant savings right up front. And again, we don't require SSD. This is just an example of what you might save. Now, in addition, it was all thin provision storage, which it wasn't before, which was also another nice savings. Here's an example of what we've been seeing in recent proofs of concept from a speed-up point of view. What this shows is they'll typically run a baseline without us. Then they install us on the same storage, and that's the performance increase they see against their existing storage. They've added no hardware. It's all thin provisions, so they get lower space consumption because they were all using thick VMDKs because they needed IOPS. And you can see the provisioning times. This is not just for creating a VM. This is for creating a VM with high-performance storage and ready for use. Okay, this happens to be a benchmark against a 1,000 desktop environment that we ran on the Hyper-V side. And I'm just going to briefly mention. So 44% fewer spindles relative to native Hyper-V. That, in that particular case, represented about, oh, again, I only know dollars, so I'll stay out of that. Deployment speeds dropped from 32 hours to 8 hours for the 1,000 desktops on the redeployment. So this is the image updates. And even against the thin provision implementation on the Hyper-V side, we needed 74% less storage capacity. So this all translates to a lot less storage. Now, I want to make a couple of comments about this because this is very instructive for what you'll need to think about as you're putting a POC together and understanding where the storage starts to fall over so that you can accurately forecast what the needs are going to be going forward. What this shows, this actually was a 2,000 desktop environment that we ran. The native environment without us could support 401 desktops in that environment. When they put us on, they could double that to 830. What's important about this is the number that you need to understand to be able to accurately forecast what your needs are going to be going out there. What ends up happening in most POCs is they've configured it in such a way that the number they've tested only runs out to somewhere way before the storage starts to go haywire. So they really don't have an idea about where things will start to fall over are. Now, how we did this, this was probably more elaborate than most people might do, but we used the VSI benchmark. And I think I saw that they've got a booth here, but basically they have a VDI benchmark that you can use for testing purposes in your own environment. And we basically just added another desktop every minute to this configuration until it fell over. So that's how we got to this. That gives you great information for understanding exactly how much your storage is going to support from a desktop point of view. Okay, in that particular case, we were able to support roughly twice as many desktops. Our software is deployed in a lot of sites out there. We've got a lot of Fortune, actually 1,000 sites. You saw some of the names on the previous slide. So what I'd like to do is I'd like to end with some best practice suggestions that sort of fall out from some of the discussion that we've had here. So it's very important to understand exactly what your IOPS requirements are in these environments and what your objectives are. Do you have certain latency requirements that you want to meet for your desktops? You know, you can have things run slightly slower than they were on the physical desktop, and the people sitting there may not be able to notice, but there'll certainly be a point at which ultimately they're going to start to notice, hey, this thing seems like it's running more slowly. And that's always the concern, in a VDI deployment, especially because of the storage performance problems, is that people say, no, I don't want to do a virtual desktop because the performance is not going to be good on it. I want my own personal desktop. So you need to sort of understand what that is. I was at a technical show a couple of months ago, and actually one of the, there were no end users at the show. And one of the VDI administrators put up something, and he said, when we roll these out, it was a university setting. He said, we don't even tell people about persistent and non-persistent or customized and non-customized desktops. We don't even use those terms, because as soon as we say non-customized, then they have a negative reaction against it. They haven't even seen it yet, but they don't want it. So he actually used some different terms to describe what it was they were doing. They actually were able to deploy with a floating model and meet the requirements of over 85% of their end users. So that's just another little trick to keep in mind there, is you don't necessarily need to describe these things in the terms that you see vendors use when you're talking to your end users. Okay, IOPS. Right IOPS are the critical ones, but you need to understand what else is going on, because you may be willing to give up some storage latency on the very high end of your right ops requirements if you can save a few bucks on that or keep the price down within your budget range, that type of thing. Knowing what the implications of thick versus thin versus link clones are. So financial implications, performance implications, space consumption implications. So you'll need to choose one of these as you deploy in the VDI environment. I've said that several times today, but I really can't emphasize this enough, because you absolutely cannot forecast what your future requirements are if you don't understand where the limits are. Okay, and then on the SSD side, SSD cache, it'll solve your read performance problem, understand its limitations. If there's a way to use it more efficiently, that's going to potentially save you a lot of money. That's a good thing to look into. And also, you really do need to work with people that understand storage sizing very well, and make sure they understand what your objectives and what the IOPS they've measured in the desktop environments that you use for early testing purposes are, so that they can help you size that appropriately. Okay, so that's all of the content that I have today. Let me open it up for questions if there are any. I can't believe I covered everything. Okay.
A couple of slides back, you talked about getting twice the desktops.
Yeah.
Per host. Can I just clarify that's per storage host?
So yeah, what this actually, in this particular case, we did not increase the CPU or memory in the host, and we kept the same storage config on the back end. But there is a caveat associated with this, so let me mention that, is that in most of the environments, at least in our experience, storage is always the first bottleneck you hit, and you can get huge benefits out of solving that. However, there are going to be situations where CPU or memory might be your primary bottleneck. And if that's the case, then something like this, which speeds up storage, is not going to have an impact. Okay, this particular impact was on a situation where storage was the problem. But we did not increase the CPU or memory here. Now, those numbers might have been higher on both sides if we would have thrown more CPU or memory into the hosts. But in this particular situation, we kept those stable, and the only difference was Virsto installed or was Virsto not installed.
Anybody else have a question?
There's one here, yeah.
Are there any limitations on the backend storage you can use?
So in our case, it has to be block-based storage. It doesn't matter what vendor it's from, and it could be SSD or spinning disk. This model right now has not been implemented on top of filers. So it doesn't work on filers, but it works on block. Yeah. Was there one also? I thought there was one back there. Did you have a question earlier? No. Okay. Okay. Yeah, so this only runs on virtual servers. Well, I should say we only sell it on virtual servers, because let me tell you what will happen on physical servers. If you do not have a very random or a very write-intensive I/O pattern, then you're not going to see speedups like this at all. What this all depends on is that's the kind of pattern your host is generating. The more the more random it is, the more write intensive it is, the better speed up you're going to get. Some of those numbers I showed earlier, like that 56x at AVG, their environment, after they reached steady state, was about 95% writes. And so they were seeing a much higher number than that 10x that I sort of used the standard marketing thing. But as this is less random and less write intensive, then you'll see the speed ups go down. So in situations where, let's say you've virtualized a database server, but you've only put one database server on each host, and you primarily virtualized it to lower the cost of DR or because you wanted to make cloning easier, you're not going to see much speed up with something like this in an environment like that. Yeah. So there's sort of that sliding scale. More random, more write intensive, you'll see higher performance, higher speed ups. Okay. Anything else? Okay. Well, thank you very much for your time today. I appreciate it.